Okay, in chapter 5, multi-machine power system stability is very important chapters or concept in power system. The power system stability summarized in uh, some lessons we get about the power system stability. The power system stability when is important when we have a disturbances in power system. For example, when we have a fault in power system fault. For example, three phase short circuit. How the power system restored and how long we can stay in faulty situation will be important. As you know, um, the power system situation could be changed immediately to instability, and in instability the angle of rotor is changed, and this angle of rotors may turn off generator, and turning off generator or power plant, it can be a worse situation, and uh, the power system could be blacked out. The blackout means that the power system begin to lose each generator one by one, and after some seconds the power system uh, no longer have any power plant, and the whole generators and power systems were blacked out and turned off. The power system stability in this case means that the stability of angle of rotor. In scientific literature, we have three kind of stability: the steady state stability, steady state stability, steady state stability. That means that the stability take long time. The number two is dynamic stability. Dynamic stability. And number three is transient stability. So we have three kind of stability in power systems, and in when we lose stability in power system, essentially we lose synchronism between, for example, two generator. For visual studying about instability, I prefer to uh, show you the two stability. For example, this graph means that, for example, the stability of delta 2 1 means delta 2 minus delta 1. What is delta? Delta means angle of rotor. In synchronous generator, we have two parts. A stator, it means a static part, and rotating part means rotor. All of these two parts have windings. The stator have windings, three phase A, B, C, and rotors have windings. The rotors turn by prime mover. With the speed of omega m. This is axis or shaft, turning by steam or wind or water or hot compressed air or etc. And after turning the rotor, the rotating field cuts the winding of stators. Phi is flux or rotating flux. This rotating flux cut the winding of stators, and in each windings of stator induces voltages, and so the three phase of ABC exist. In this case, the angle of rotors is very important in stability. For example, if we have two generators, we have for each generator a, an angle. For example, delta 1 for G1 and for G2 delta 2. For stability studying, the difference between two angles have to study. For example, uh, in studying the difference between angle of generator 2 and 1 or delta 2 1, we draw a graph like this, and delta 3 1 means delta 3 minus delta 1, and this graph is here. In some case, you see that delta 2 1 delta 2 1 delta 2 1 is not limited and increasing gradually, but delta 2 3 1 is limited or oscillating between two bonds, but the oscillation is limited. But delta 2 1 is uh, increasing. This power system is unstable, but this power system is stable, but oscillation stability. And this chapter we try to find out which situation we have stability and which situation we have instability. Okay, so we can find out the synchronous between two generators means delta I minus delta J. If delta I minus delta J is limited or oscillation in limit band, this means that the synchronism of generators is established, but delta I minus delta J is not limited or gradually increasing. This means that these disturbances make the power system unstable. In steady-state stability, the amplitude of disturbances is small. and gradually imposed to our system. For example, the increasing loads in power system or decreasing loads in power system. In dynamic stability, the amplitude of disturbances is small, but suddenly imposed to our system. And our power system lasts long time. In transient stability, the amplitude of disturbances is very big and suddenly imposed to our systems. For example, the three-phase short circuit. In this chapter, we studied the transient power stability, and suppose that, for example, a short circuit is happened in somewhere in power system, for example, in a bus somewhere in power system, and we should study about how long these short circuits maybe maybe exist, or the protection systems when take a time to cut the transmission line, faulty transmission line, to save our generators from instability. Okay, when we want to study a single machine, a single machine, for example, the generators, in relation between a infinite bus, we call this infinite bus. This is generator. This is called single machine, infinite bus. This means that SNIB. SNIB means single machine infinite bus. Single machine means one machine. What's what is infinite bus? Infinite bus is a bus. Is what is the infinite bus? Infinite bus is a bus you can you can no. Infinite bus means that if you get how many you want active power without any decreasing frequency, or reactive power without any decreasing or falling voltage. It means that infinite bus. For example, if you have a outlet, do you know outlet in your home? Outlet in your home, and you uh, or in many cases you can say plug in your home. If you use this plug in your home and uh, how and you can give this plug many active power without falling frequency, or give many reactive power from plug without any decreasing voltage. This plug in your home means infinite bus. The behind of infinite bus is a very big power system. For example, in behind of your infinite bus is multi-thousands megawatts, and how many the active power you use, you don't experience any decreasing frequency or decreasing voltages. This means you get the infinite bus. When one generator is connected to infinite bus, is called as single machine infinite bus, or SMIB. In the simple case, we studied single machine infinite bus, and in advance we will study multi-machine infinite buses. In assessing or for assessing transient stability in single machine infinite bus, we have to consider some assumption. The first one is a period of time is called pre-fault time. For example, if you consider this axis as a time, this time is 0, and the time this time is fault time, or in this time the short circuit is happened. But before this time we called pre-fault, and in this time we have any faulty situation or any short circuit. In this time, in this period of time, the delta, the angle of rotor, is constant, and in pre-fault every situation is stable. We experience a stable situation in this period of time. The consumption of 2 after after uh, after happening a fault, for example, the three-phase short circuit, we have a new period of time is called to DUF. DUF means during fault. The fault happens in t equal to 0 and lasts to TC. TC in TC time. In TC time, the fault is clear. In this time, fault happens. In this time, fault is cleared. After the clearance of fault, we call that post-fault. Post-fault means that POF. In this period of time, we have any faulty situation and we left behind the during fault. If we have delta 1 in pre-fault, in post-fault we experience delta 2, and delta 1 is another, or delta 2 is another one. If delta 2 means that delta of a machine in post fault situation. Post fault situation. This delta 2 is very important. If delta 2 is not limited, it means that our machine or generator is unstable. If delta 2 is limited to a number, for example, delta 1 is 30 degree and delta 2, for example, is 40 degree, this means that our machine convergence in another delta, and it means that our machine is stable. And after experiencing during fault, our machine has a new angle, but this angle is limited and fixed, and this means that our machine is stable. So The time between 0 and Tc means during fault, and the time is bigger than Tc means post-fault. In post-fault, the short circuit is cleared. For example, because of acting uh, relays or opening circuit breakers. Opening circuit breakers after fault. This means that post-fault. Okay, for modeling generator, we have this kind of circuit for modeling the generator. E prime with the angle of delta means that electromotive or internal electrical voltage of generator is called E prime. E prime means transient mode of internal voltage of generator with delta. Delta means the angle of rotor. Angle of rotor. In modeling a generator, we have to consider impedance of generator called ZS prime. Prime means transient. Prime means transient. The ZS prime consists of RS resistance of synchron resistance and X prime D. X prime D means that the transient of reactance. Transient reactance. Reactance, transient of reactance. This is equivalent of generators. We consider the input power of generators, for example, in a shaft or turbine. The input power of generators is fixed, and the field current of generators is fixed. IF is fixed. IF means field current or excitation current. What is the excitation current? If you remember what I say about generators here, this means excitation or field circuit. The current of excitation circuit is IF. The current of excitation circuit is IF. The changing IF, if IF change, increasing or decreasing, so the flux of generated by this circuit can be increased or decreased. So the IF is very important for controlling the flux, and this flux control E prime, and we can increase or decrease E prime. So in this note, we consider the field current or excitation current fixed. So in power system, the excitation circuit has the current of IF. The IF make flux, and the flux make E prime. Which E prime? This E prime. The E prime made by flux, and flux made by excitation current. This side is in rotor, and this side is in stator. Okay. In this case, we have M times of generator. Generator number 1, 2, generator number M. These generators is connected to a power system networks with N buses. We name the generator bus as number 1, number 2, number 3, or 2 number M. And we have N buses in transmission lines. For example, a voltage of generator number M plus 3 is magnitude of voltage M plus 3 with the gamma M plus 3 as an angle of this voltage, or the apparent power of bus M plus 3. We have active power plus J reactive power. It means that voltage multiple to conjugate of current. If we have a load in this is load in bus of M plus 3, for example, we have to model is as admittance by dividing current to voltage. It means that P minus JQ over V square. For assessing the stability. In that case, we uh, explained we have to replace the generator with its electrical equivalent. This is electrical equivalent of each generators. After this equivalent, we have bus number 1, 2, 2M, and another bus in transmission line of networks M plus 1, M plus 2 over M plus M plus M, and N buses in transmission networks. Each generators has input active power as prime mover. P input of 1, P input of 2, P input of 3, and P input of M generators. Okay, after that, we can model the transformer which is connected between the generator model and power system. This is transformer. The transformer is modeled as a single reactance J X T, and can be right here. The transformer is connected between the electrical equivalent of generator and the rest of networks or power systems. After that, we have to model load. This means loads. This is load. This is load. We model loads as admittance in the stability studying. In this case, we learn about when you want to study about the stability or transient stability. The transient stability you should study about delta. For finding delta, you have to solving differential equation Differential equation on which parameters? About the changing delta. The SMIB, single machine infinite bus, has a equation has a equation as a differential mode of delta. For example, d delta dt or d2 delta on dt2. And after solving this non-linear differential equation, we can write delta t, and after that we can write delta of a generator minus delta another generator, delta n minus delta n, for example. And you can draw this differential, this subtraction, the difference between two delta, you can write it, or you can draw and graphically see that these two generators keep synchronous or not. If this difference between two delta of two generators is limited, or its oscillation is limited, this means that we have stability between two synchronous generators. If this difference between two angles is gradually increased or decreased, this means that we have any stability in power system. We see this graph. For example, delta 2 1 means delta 2 minus delta 1 is increasing gradually. This means that unstable. But delta 3 minus delta 1 is oscillating in limited band. Okay. Please pay attention regarding this power system. Okay. For the studying stability in a power system like this is very important to pay attention that you have to install mathematically a bus on the first part of each generator. Each generator has two parts electrically: a voltage source and connected reactance. But we have to set a virtual buses between them and numbered from 1. This work is done for all generators. So we have to consider a bus mathematically, imaginary, in your paper, not in real case, between the voltage source of generators and its reactance, and numbered from 1 to m. We have m generators, and so we have m buses. After that, we numbered m plus 1 after the reactance of synchronous generator, m plus 1. This is very important for stability studying. So in stability studying, we add some buses where between voltage source and reactance of generator, and numbered from 1 to m. After that, we rename the buses before transformer as m plus 1 to m plus m. And after that, we numbered as routine in transmission lines. This is very important. This numbering is very important for stability studying. In stability studying, we are interested to study on behavior of delta. The delta and how delta is behavior is very important to us. So we have to set a virtual buses near the voltage source of generator, near the angle of rotor. So in this case, we have to, after this setting buses, we have to write this equation. What is this equation? This equation is regarding matrix I equal to y bus multiple to matrix of voltage of each bus. The y bus in stability called as y bus stability. The y bus of stability, y bus in stability study is not equal to y bus in load flow study. In stability, we add some buses here. In load flow, we consider the synchronous generator and transformer as ideal source. You in load flow ignore the generator and its transformer and change it to ideal form of source. But in stability, we add some buses to find out how the voltage and its angle behave in post-fault, in during fault, in pre-fault, or other situation. So, in this case, for in this case and for in this case and for this equation, the I is injected current of each bus. The bus number one is a generator bus connected to voltage source, and we have current. Bus 2 is like bus 1, we have injected. Bus 3 is injected, bus M injected. But M plus 1, we don't have any sources in bus M plus 1. The injected current from a source in bus number M plus 1 is 0. We don't have any injected in bus M plus 1 to M plus M or each buses except the bus number 1 to M. The only bus number 1 to M, because of connecting the sources in these M buses, we have current. Other current is 0. Other current is 0. In voltage matrix. In voltage matrix, the voltage of bus number 1, because of connecting to source, generator source, is E1 prime. The generator 2 is connected to bus number 2, so the voltage of bus number 2 is E2 prime. To bus M, the bus M, the voltage is EM prime. E1 prime to EM prime. But other voltage of bus is named Vm plus 1, Vm plus 2 to Vm plus M plus N. This called E, this called V. So this equation can be right here. I sum array is I, sum array is 0. V sum array is E, sum array is V. So This admittance matrix is divided to 4 sections: section A, section B, section C, and section D. Some section is about the relation between Mi to Me is named section A, or submatrix of A. Some relation between I and V is called one submatrix of B. Relation between D0 and E is called submatrix of C. The relation between the 0 matrix and the V matrix is submatrix of D. So in stability studying, we have to write this matrix. This matrix is very important to stability study. The question is, which part of this matrix is very huge, which part of this matrix is important to us? This part of matrix is very important. I, because of injection of current of each generators, and E for evaluation of voltage of each generator and changing the amount of voltage and angles. The otherwise is not important for us, and we try to simplify this matrix to a smaller one. So this matrix is I0 equal to divided 4 submatrix A, B, C, D, and a matrix is V and E and V. This is important. This is important. And otherwise is not important. We have to simplify this matrix. For simplifying this matrix, we use a reduction mode. If you extract I is A multiple to E prime, this B as a submatrix of Y bus multiple to V. In this case, 0 equal to C multiple to E prime D multiple to V. We can write like this. In this case, we can write V as minus inverse of D multiple C multiple to E prime, and after substitution or replacing V as these terms, we can get matrix I is A minus B multiple inverse of D in C, all multiple to E prime. This called matrix reduction. Matrix reduction. And you can change this form of matrix to this form. I Y bus reduction in E prime. This is new formula. This is Y bus reduction. In evaluation of transient stability in three period of time, pre-fault, during fault and post-fault, we have three nodes. In pre-fault, it means that the times before than 0, the matrix of Y bus total and Y bus reduction, we have two Y bus. Also in during fault, we have Y bus total and Y bus reduction. In post fault, and we have two Y bus. Y bus total and Y bus reduction. So, in synchronous machine, synchronous generator, we have very important differential equation. It's called that the rotation or oscillation equation in synchronous machine or synchronous generator. D2 delta on D2 equal to P Fs on H, P input minus P output. The second time of derivative of rotor angle is equal to P on synchronous frequency. For example, in Iran or Iraq is 50 Hertz. Fs is 50 Hertz. H is means inertia, and this means inertia of rotor, and P input is the power of shaft or turbine that imposed on a generator shaft for turning the generator, and output is electrical output of generator. So This generator have mechanical input and electrical output. And this differential equation is valid for synchronous generation. After solving this equation, you can get delta t, and you can draw delta over t and its isolation. For example, in pre-fault we have this delta, and during fault we have some oscillation, and after fault or post fault we have another level of delta. This is delta, for example, delta 1, this is delta 2. This is oscillation. The changing between delta 1 and delta 2 is acceptable. The situation of power system is changed, so the delta is changed. But the delta 2, if a delta 2 is not limited or not set a new point, for example, after this oscillation we have a very big oscillation, or the amount of delta gradually increased or decreased, delta 2. This delta means that your generator is unstable. But fixing in a specified value after fault, for example delta 2, is stable. The behavior of delta is gained by solving this differential equation. In this case, for M generator, we have M differential equation. Differential equation for generator 1, generator 2, generator M. This is input mechanical power of generation 1, generation 2, generation M, and electrical output power of generator 1, 2, or M. The output power is electrical. P input is mechanical. P output is electrical. The output of power can be written as E prime multiple to conjugate of current. The current, injected current, we discussed before. The active output power is a real part of this term. And so the active power can be write as KCl4, and so in load flow we had this formula as output electrical power of each generator. Sigma EI prime EJ prime is neighbor voltage. Yij reduced in cosinus of delta I minus delta J minus theta Ij. We studied this equation in load flow. And so we can substitute the last equation in oscillation equation differential equation of generator. In generator we have d2 delta on dt2 is pfs on h. For example, in generator number I we have hi p in generator I minus P out generator I, and for P out generator I we can say that sigma delta EI prime EJ prime in Yij reduced in cosinus delta I minus delta J min minus theta Ij. EI prime and EJ prime is get from load flow in pre-fault. This is very important. EI prime and EJ prime from load flow and in pre-fault mode, and fixes delta I and delta J from load flow in pre-fault we received, and Yij reduced and theta Ij from Y-bus pre-fault reduced as drive. And so we have two set of equation, differential equation. The d delta on dt is omega I, and d omega I on dt is pfs on hi minus p input minus p output. If omega I is d delta I on dt, so d2 delta I on dt2 is d omega I on dt. So we write d delta I on dt2. Okay, so in this chapter, in this class, we studied on power system stability, especially when a disturbance is happened, and the disturbances is happened in this time, this period of time, and this period of time is very important for finding the final angle of rotors, and the pre-fault period of time is very important to calculation. In pre-fault we have a delta, for example delta 1. During fault the delta is changed or oscillate, and after the during fault we get delta 2. If delta 2 or situation number 2 of delta is fixed, it means that your synchronous generator is stable. If delta 2 oscillate or gradually increased or decreased, it means that your generator is unstable. We studied in this session about this concept, the concept of stability, the equivalent circuit of generator, and we try to renumber the generator with equivalent and transformer as a new buses. We get new buses in each generator. This buses is on your paper, not in real reality, but in your paper, and number from 1 to m. This is because we very interested to calculate the amount of E with its angle called delta. Because of these parameters we have to set or install new buses mathematically and numbered from 1 to m, and we have to renumber all buses in power systems. And after that we try to establish new Y bus that is called Y bus used in stability, and essentially different from Y bus we use in load flow. In this Y bus and this equation we have some arrays in section of current as injected current of each bus. That's injected current of each bus is only for generator bus. Another array of current will be 0. In the voltage bus, the voltage of generator bus is called E prime, but other voltage is called V. And we can see that this equation is very big, and we try to reduce this equation. After reducing this equation we get Y bus stability reduced. The Y bus stability reduced is calculated in this case in this formula, and after that we studied about the differential equation of oscillation of generators as the second type of differential equation, d2 delta on dt2, and we introduce P input as mechanical power, active power, and P output as electrical power. And for electrical power we substitute the electrical power PO as its results catch from load flow, and we can write a set of a differential equation like this. In the future we try to solve this set of equations to finding the oscillation of delta and finding that uh, your generator remain stable or not. Thank you for coming in my class and uh, listening my teaching about the power system stability. You have any question? Could you please ask your question again? Okay, do you have any questions? Thank you very much. Have a good time. Bye.